Now let's consider friction, in particular dry friction, friction without any type of lubrication. After this, you'll have a good idea of how friction works. You'll be able to draw free body diagrams to include friction and hopefully be able to solve problems involving friction. As usual, there are several examples, group problem solving exercises in the slides that you should go through on your own. And of course, the quizzes are on the course website along with my example problems. So what applications are there of friction? Well, friction's all over the place. Friction is something that is actually a reactive force, which seems a bit strange given this example, because you think it's something that you apply. And in a sense, that's true, but you'll see how friction's actually a reactive thing here in a moment. But if we're going to use friction for useful applications like brakes on cars and bicycles, we've got to understand how the frictional forces involved behave and what they do. So how could we determine the magnitude and direction of the friction force? How is that done? You might have the idea that it depends on how hard you press the brake pad into the side of the wheel, and that is true. That does make a difference. And we'll discover exactly how that's related here in a moment. Other applications. Here are ropes being used to pull a refrigerator across the floor. Well, is it going to slide or is the thing going to tip? And by the way, would it be best to pull up on the rope, pull down, pull horizontally? What would be the best way? What do you think? This is something that involves friction, of course, and it'd be nice to understand how the physical parameters of the problem relate to the solution, to what will actually happen and predict what will happen with friction. So, characteristics of dry friction. What is friction? Well, it's defined as a force of resistance acting on the body which prevents or resists the slipping of a body relative to a second body. What the heck does all that mean? Friction resists motion. That's what it means. Friction simply resists motion. So if you notice, we've got a block here on the floor. We're trying to pull it to the right with a force P, and friction will resist that, right? Even whether the box is moving or not, friction will resist it. Now, here's something interesting. What if there were no force P? Then how much friction would there be? The answer is none, because friction is a reactionary force. So in other words, as you pull on that rope or whatever is attached to the box or push it, friction will increase equal to the force that you are pulling with or pushing with until friction can no longer resist anymore and it basically yields. You'll see that in a minute. What is true about friction, though, is that it acts in a direction that is parallel to the surface of interface or tangent to that surface. And so it's simple to see this box interfaces with the floor just along a horizontal line. So friction will act along that horizontal line. What if the box were something that was round, that was not rolling, but was just sliding back and forth? Well, in that case, friction would still act in the direction along the floor, because that's what defines the shape, that controls the motion. So friction has more to do with motion or impending motion than anything else. And of course, motion is controlled by the shape of the interface between the two objects that are slipping past one another. So for a box like this, or any body to be still, in other words, static and not accelerate, the amount of applied force P would have to be equal to the friction. Because look at this simple example. We've only got forces in the horizontal direction that are the pulling force P and the frictional force F. To keep the box from accelerating, those two have to be equal. Now, the box could be moving. That's okay, but P would still have to be equal to F. Otherwise, the box will start to accelerate, and that's a different class. That's dynamics. I'll let you worry about that one later. For right now, it's statics. And for static equilibrium to be satisfied, the pulling force and friction force have to be equal to each other, which again suggests that friction is a reactionary force, because you get to decide how hard you pull, right? How much force P you apply to it, and then friction reacts to that. Another thing that has to be true is that the normal force has to be equal to the weight force. Now, be careful about this. Students in statics get stuck in the mode that normal force is always equal to weight force. That's true for this class. When you get to dynamics, that's not true. If a body is actually accelerated in the vertical direction, either upward or downward, the normal force and the weight will be different from one another. So be careful with that. Hopefully you remember once you get to dynamics that normal force is not always equal to weight force, but I'll remind you then as well. But for now, for static equilibrium, the amount of force that the ground pushes up on the crate with has to be equal to the weight of the crate. Otherwise, if there was an imbalance, the crate would accelerate upward or accelerate downward, depending on how the sum came out, whether it was up or down. Now, of course, the normal force is a reaction force as well, and so the fact that it can come up to the weight, assuming the floor can support the weight, they just naturally equal each other. Another thing, though, is that the moment of the weight and the moment of the applied force have to be equal to each other. Now, this is a different thing. Notice that moments are being summed about point O, and x is simply the offset distance of the normal force from the weight force. Because if we weren't applying any force to the crate to get it to move, no force P, then there would be no friction, and the weight and normal force would simply be in line with one another, because this would have to be a two-force body. However, since we're pulling on it, the normal force has to move off from under the center of gravity of the object, because the applied force P and the friction force F generate a moment, or a force couple, a moment that has to be resisted by the weight and the normal force. And the only way for that to happen is for the center of the pressure, because really there's going to be a pressure underneath the entire crate, and depending on how weight is distributed and so forth, that pressure distribution is going to change. But we can integrate it, we can add it all up into one resultant force, which we are calling the normal force, and the location of that normal force can actually move around. So the last equation is a moment equation requiring that the moment of the weight and the moment of the externally applied force P about O must equal one another for static equilibrium. Now, if we do this experiment, if we set this crate on the floor, start pulling it out with force P, then we know that if the box or crate, whatever you want to call it, if it doesn't start moving, then as we apply more and more force, something is resisting it more and more, and that something must be friction. And so we can plot the friction, as you see at the beginning part of the graph, as equal to force P. The horizontal axis is force P, the vertical force is the reactionary friction force. And so you notice the friction force and the applied force P are equal to each other, and so the line simply moves at a 45-degree angle. Now don't worry about Fk yet, because that comes later. Right now what happens as we apply more and more and more pulling force P, what happens is the friction increases farther and farther and farther and farther until finally it gets to a maximum force F sub S. Now there's a subscript on that force, that frictional force, you might have noticed it, S, versus the other subscript K. One stands for static and the other one stands for kinetic. Basically, we always break down the friction into two parts. The first part is where no motion occurs, where there's no change in motion, I should say, where there's no acceleration. That's the first part. That's the so-called static part of friction. As you continue to increase the pulling force, eventually the friction will give up. It cannot resist the pulling force, and the body will begin to move. When that happens, an interesting thing occurs. The amount of force that friction applies, because there's still friction, but the amount of force it applies drops down a certain amount to F sub K. So actually, the frictional force will apply more force while the box is not moving, or has the ability to apply more force while the body is not moving, than when the body is actually moving, which is an interesting phenomenon, but that's the way things actually go. So you'll notice that our graph is broken up into a no motion and motion section, and we don't mean motion in that it's accelerating, but that it's sliding past something, right? That the friction is due to a sliding motion, not just a static motion. Right. Static motion, I guess that's an oxymoron, right? A contradiction in terms. So if we assume that tipping does not occur, and we plot this graph and apply the force P as it increases, this is what we'll see. This is the response of it, the pulling force versus the frictional force. Now, why they have the graph dropping off at the end, I don't know. I'm not familiar with that part of it. We're not going to dive into that. Maybe as you pull harder and harder, the friction force reduces, but I've never heard that before. I think that's not intentional in the slides. I can be wrong. I don't think the book discusses it either. So notice that the maximum friction force occurs right before the box begins to move. This is called impending motion. You can figure out the value of the frictional force. It's actually really easy, because at that point, the frictional force is equal to the friction coefficient times n. Now notice mu is the friction coefficient symbol we use, and the subscript s indicates static friction. Now you may have taken physics and already have seen an equation that looks like this that says the frictional force is less than or equal to mu n. That one is correct, and this one is too, but they're talking about two different things. Well, I guess the other one's more general. This is more particular. This is talking about the point right before slippage occurs, whereas the other equation with a less than or equal to sign is talking about the entire curve from no pulling force being applied all the way up to the maximum pulling force before friction kind of gives way and the box starts to slide and slip. So the friction coefficient is not a function of just one of the two materials that are in contact. It's a function of both materials. Rubber on rubber has a different friction coefficient than, say, rubber on cork or rubber on steel or steel on steel. It's not like you can take a coefficient for steel and a coefficient for rubber. That's not a thing. It's a coefficient for rubber and steel together, or rubber and rubber together, or so on and so forth. So the friction coefficient depends on both of the materials that are in contact with one another. But be careful, because the maximum friction force does not always have to be applied. I mean, think about it. If you set a book on a table and the table's flat, how much friction is there? Well, you might try to calculate it with this equation, because certainly you can measure the friction coefficient, you can measure the normal force, it's equal to the weight. But if you multiply the two together and say, well, there's your friction force, no, I'm not applying any external force to the book. Friction is a reaction to an external force trying to slide the book across the table. See, so that's why friction is less than or equal to mu n. This just gives us the maximum that the static friction can go to. Now, once the box begins moving, as I said before, the amount of frictional force drops, and now you have to use the kinetic friction coefficient, mu sub k, and it's less than mu sub s. So if you ever calculate a force in motion that's greater than the static force, or the maximum static force, try one more time, the maximum static friction force, then you know you've done something wrong, because this is true of all materials I know of. It's really important to remember that the friction force can be less than that maximum. So don't assume that the frictional force is equal to mu n unless you know that motion is impending. The key words with friction is impending motion, okay? So how would we come up with this value of friction coefficient? Well, it's actually pretty easy. There's a couple of different ways to do it. If we want the static coefficient, then we need for the box to not be moving. And so when the box is on the verge of sliding, we know that the normal force and the static friction force combine to create a resultant. Now that resultant, it's force from, whatever is supporting the box. I don't like thinking about this way. You'll see the way I like thinking about it on the next slide. But basically they combine together and they form an angle phi sub s. That's what that funny looking symbol is. It's called phi. It's a Greek letter. Phi sub s is just the angle of the total reaction, because the reaction consists of both a normal force, that's a reaction to the weight, and a friction force, that's a reaction to the pulling force P. So you may as well combine the two into a resultant that is a reaction, right? And then from the figure, you can see that the tangent of the angle is equal to the friction force divided by the normal force. But since we're on the verge of slipping, since impending motion is where we're at, and it's just about to move, then we can replace the frictional force with the friction coefficient for static friction times the normal force. The normal force cancels, and it yields the friction coefficient. Now, if you were trying to perform this experiment, what I would suggest you do is measure the weight of the object, know that that is equal to the normal force in this case, and then measure the amount of force P required to get the thing to start moving. Maybe you have a gauge or something that is set so that it registers the maximum amount. As you pull, the needle goes up, or maybe the reading on a digital scale goes up, and it remembers the maximum value that it gets to. There's ways to do that with an analog scale, with a needle, and or with a digital scale. But basically, you just pull on it until it slips, and then just remember the maximum force reading, and then all you have to do is put the force reading you have in the numerator, the weight of the device in the denominator, or the crate in the denominator, and that ratio is the friction coefficient. So it's pretty easy to determine. But there's another way to do it, and I really like this way better. I don't know, maybe it's because it's the first way I learned. That is to take the block that has some weight W and put it on an inclined plane. And what you can do is actually take that plane and start to increase the angle of the plane right when right until the block just begins to slip. What's nice about this is if you think about the free body diagram of the crate, the only thing preventing the crate from sliding down the incline is the friction force. And so as you increase the angle of the incline, what happens is the friction force is having to resist more and more of the weight. Because think about it, the normal force plus the friction force have to add up to compensate for the weight. And so what happens is as you increase the angle, you require more and more friction, but of course you've got less and less normal force because the angle of the normal force is changing and not resisting the weight as much. Now, in math, we sum forces in the vertical direction and the horizontal. However, what's done here is we rotate the coordinate system so that it's easier to sum these forces in the vertical and horizontal direction. What that means, though, is that horizontal and vertical is now inclined at the angle theta sub s. If you're not familiar with Greek letters, that letter for the angle is theta. But anyways, the angle for static friction. And of course, the weight is being broken up into components along the incline and normal to the incline. And those are the directions x and y that are being summed. Anyway, when you put those two equations together, what you'll find is that the friction coefficient is basically the weight times sine of the inclination of the angle divided by the weight and divided by the cosine of that inclination angle. Of course, the weight cancels and sine over cosine is tangent. So all you've got to do is put the block on an incline, start to incline the block on the incline. Once it slips, just measure your angle and take the inverse tangent of that angle, and boom, there's your friction coefficient. So I like that one, I guess, because, I don't know, you don't require a scale to do it, right? You don't have to measure the weight of a pulling force, and you don't need to know the weight of the object either. All you need is the angle where it starts slipping. So that makes it, I think, easier. So do we have sort of a recipe or a cookie cutter approach to solving problems with dry friction? First, draw the free body diagram and put friction on the free body diagram in the correct direction. Now, this requires that you know which way friction is about to occur. And be careful, because it can be really confusing as you think about an inclined plane and a box on it, and you think about, well, where's the force on the box? Well, if the box is, I don't know, I'll use my calculator for a second. If the box is my calculator and starting to slide down, which way does friction act on the calculator? Well, it acts up. And you can imagine that because think of the relative motion between those two surfaces. You can think of the inclined plane as coming up, or the calculator or box is coming down. And so it's the motion of the body that we want the force on. We want the force on the crate or the calculator, whatever's sliding down the incline. And so motion is in this direction for that body. It's down the incline. Therefore, friction is the opposite, you see. And it doesn't have to be actual motion. It can be motion that's about to happen. That's called impending motion. So just make sure that you draw your frictional forces in the opposite direction from where either motion is occurring for the body you're drawing the friction force on, or about to occur, impending in other words. Then finally, well, not finally, but next step, determine the number of unknowns. Don't assume that the frictional force is equal to mu times the normal force unless motion is about to happen. In other words, unless there's sliding that's about to occur. That's the only time when the friction force is equal to the friction coefficient times the normal force. Often in a problem, you're given the friction coefficient. And coming up with the normal force is pretty easy usually. So the temptation is to automatically just say, well, I know what the friction force is, it's mu times n. That's not necessarily true. Remember my example of a book simply sitting on top of a horizontal table where gravity acts normal to it. It's not going to move because there's no force trying to make it move. Therefore, there's no friction on the book between the book and the table. I should say there's no frictional force between the two. Finally, apply the equations of equilibrium and solve for the unknowns. And that's what you need in order to work problems involving dry friction. There's another type of problem that deals with friction that asks the question, okay, so we've got this body that has some size. We're pulling on it. Will it tip over or will it slip? What will happen? And so if you think of just a simple box, how can we determine whether it will slide or tip first? Now, if you think about the situation, we've got the weight of the box. We've got a force P being applied to it, and then frictional force responding at the bottom, and of course the normal force at the bottom of the box. The problem is we don't know several things. We don't know the friction force, right? We don't know the normal force. You can say, well, the weight and the normal force equal. Yeah, that's true, but that's one of your equations. That's the sum of force in the vertical direction equation. We only have 3 equations of equilibrium, so one's going to be used up to figure out the normal force in terms of the weight force, and maybe part of the applied force P. But if you count them up, you'll find that we have too many unknowns. We've got the friction force, normal force, position of the normal force, that's the new one, and the externally applied load, P. And our question is, does it tip or does it slip? So it turns out what we have to do is to make an assumption to get another equation. So we're trying to get a friction equation that we can involve. And then we'll have to go back always and check to see if our assumption was true or not. So if we assume that slipping occurs first, if slipping is going to occur, what does that mean? Well, that means the friction's at its maximum, and therefore the frictional force is equal to mu n. There's our other equation. And then we can have 3 other equations of equilibrium, right? The sum of forces, horizontal, vertical, and then a moment equation. And we can solve for the unknowns. For example, where is the normal force applied to the bottom of the box? What's the the externally applied load P and the normal force. And then after we solve all this, we can determine, well, is the position of the normal force still under the box, right? Or did it move out from underneath the box? Because if it moved out from underneath the box, our assumption for slipping was wrong and tipping will occur. On the other hand, if we assume tipping occurs, then what that means is that, think about it, that means the normal force is all the way at a corner, right? It has to be, because that's the only way that tipping can occur. Because then we would have the ability for the weight and the pushing force to not, the moments of those two to not cancel. And so if that's the case, because remember, the position of the normal force is determined by a sum of moments equation, right? The moment of the externally applied load P and the weight W, those two things are both working against each other, the pushing force trying to cause tipping, the weight trying to prevent it. And if we get to a point where we're about to tip, what that means is now those two have to go out of balance. And so the only way we can have force applied at the bottom of the crate is if we're touching the crate, right? And so the farthest out the normal force can go is out to, B over 2 in this case for X. So then we can solve for the pushing force, normal force, friction force, and then what we have to do is check to see if the friction force is below its limit. So we know the friction coefficient typically between the floor and the crate, for example, and so we can ask the question, well, if tipping occurs, then the friction force has to be less than this amount. And if you find that's not true, then instead slipping would occur. Because basically what this means is that you don't have enough friction to cause tipping, therefore slipping must occur. Your assumption was wrong.